Okay, 7:30. Today we are going to see hazards but we don't really encounter structural hazards with the small subset that we're working with. But we just need to know what they are. And we do have data hazards in our pipeline. And we talked about what they are and ways of how to handle them on Monday. And today we'll go over a few examples and walk through the pipeline. How it's exactly. Here is an example. So clock cycle 3. Right? So clock cycle 3, so like 1, 2, 3 instructions in the pipeline. Right? And we can see the sub instruction, it's RD, or its destination that it's going to write to, is register 2, and this AND instruction wants to read from register 2. Okay. So what we figure out here in the AND instructions decode stage is my RS is matching the destination register of an instruction in front of me. So if I read RS from here and I get the value out of it, it is the incorrect value. Okay. So what happens is I'm allowed to read it because I know that the sub instruction will finish and have its value ready in this register now. Right? It's right here. This is our result, right? So this result goes into both the first inputs as well as the second inputs of the ALU, and the forwarding units. It sees here register 2 is the destination register, and from here register 2 was my RS. So then the forwarding unit says they're matching. It matches at RS. And I am indeed going to be writing, right? That's also from this register. So we should select this new value rather than what you read. See that? And the reason that it goes to both of them is that you can match on RT, right? It's not always RS. RT could be the one that needs to be changed as well. So we see exactly how this forwarding unit works and how it just on the fly is going to throw away the old value that was input here and use this new value from this register. And we have the same capability on the write back stage. Right? So let's see this capability from the write back stage. Right, the AND is done. It did it, it executes, right? So it doesn't need register 2 anymore. But now we have this OR in the execute phase. And it wants to read from register 4 and register 2, and that's what it did in the previous clock cycle. But we know that register 2 was going to be updated. It's still not updating from the sub instruction, right? But we have the value from this register, right? And then we also want to read from register 4. And is writing to register 4. Let's just look at the and first, right? So just like before, register 4 is my destination. And over here, register 4 is my RS. And this instruction is indeed writing the register file, right? So the forwarding unit says, for RS, use this new updated value, not what you read from the register file. And then over here, the sub is writing, its destination is register 2, RT is register 2. So please use this new value coming from the output of this mux rather than the old value you read from the register file. Right? So this forwarding unit is responsible for figuring all of this out. Okay? And we talked about the equations that are used in order to check, are these things equal? Is it writing? Then I need to replace the appropriate value. Right? And you can make a truth table about all of that and implement this forwarding units with combinational logic. Right? All right, here's the last one. We have this add, and it's reading from 4 and 2 as well. But it only needs to forward 4 because it got 2 straight from the input of the register when it was decaying. So the value and the previous cycle here, right here as the right data. So rather than giving it the old value from the register file, it just forwards right through here, right? So that's why we're not forwarding, or we don't need to forward for register 2 down here. But we still need to forward register 4. Okay? And we have register 4 matching RD of the OR instruction and the AND instruction. Right? They're both matching with RS. So when this happens, which one do we take?
First one.
By the first one, which one?
Or
No, yes. So the newest one. Because this one is technically the first one. So the newest one is the OR. And then we select that value from the mux, right? So this is forwarding. Do we all understand this data path? So one thing that we need to note is, what if the instruction is a load? Well, if that is the case, when is the data available from the load word?
right back.
After the memory stage, right? So that's how many cycles later than an R type?
1.
So with R types, even if we had an immediate dependent instruction, because the dependent instruction doesn't need the value until executes, and the R type is done right after executes, we don't need to stop. Right? We can just forward immediately. But if we have an immediate dependent instruction after the load word, and we need that value in executes, but when we're in executes, where is load word? in memory, so it doesn't have the value yet, right? So in this case, what do we need to do?
All one cycle.
All one cycle. So here we have the load word. And then when we're in the decode stage, we would fetch the sub instructions, right? And then when the load word is in execute, we're performing decode, right? And it's inside this decode stage that we see. I'm trying to read from register S0. The instruction in front of me is a load word, and it is writing to register S0. If it's a R type, I have no problem, right? But since it's a load word, I know based on my architecture that I have to stall one cycle, right? So in this cycle, we figure that out. And in the next cycle, we just redo decode. And that's how we implement our stall. Okay. And now by redoing decode, and then whatever was being fetched in the previous cycle is redoing its fetch, right? Because we're still using up decode. So everything behind us has to redo what they were doing too. And now we can just forward from the memory and write back register straight into our executes. And again, just one thing to note, the hardware does not know about this stall until which cycle?
The decode.
Decode of? Yeah, and which cycle is that? This is first cycle. This is second cycle.
Third cycle.
The third cycle, right? So although this diagram is showing it kind of like here, right? What we would show on our tables for homework and exams is fetch here, decode here, fetch here, the other instruction, redo decode, redo fetch. Okay? You would not show it as I preemptively know before I even fetch the sub instruction, I'm putting a stall here. That would be Euler based implementation. Okay. So now we have this hazard detection unit. Does this tell us if we need to stop? Right, and what goes into this hazard detection unit? My current instruction, RS, RT, right? The destination register of the instruction in front of us, right? Which is RT for load word, right? We're checking if they're matching. As well as is the instruction in front of us reading from memory. If they're reading from memory, that means it's a load word, right? So if that is the case, where this RT from the instruction in front of us is reading from memory and it matches RS or RT of our instruction, this hazard detection unit tells this MUX, I'm not going to go forward with the normal control signals. Set all of my control signals to 0 to insert the stall here, like a no operation here. And then it also tells this register, I'm going to redo decode. Do not let the instruction being fetched overwrite my value. Please refetch the next instruction as well. we see it inserts a no-op with the 0 control signals, stalls and redoes decode by not letting this register write, stalls and redoes fetch by not letting PC write. So we see this hazard detection here. All right. So here we go. And we have this load word, right? And right afterwards, we have the and. The and is going to read from register 2, which the load word is writing to. So we fetch the load word. Okay. Decode load word, fetch the and. Execute load word, decode the and. This is the stage where our hazard detection unit is in, right? Hazard detection unit sees the instruction right in front of me in execute phase. RT is 2, which matches my RS. And it's also reading from memory, so that means it's a load word. So that means that the data is not going to be ready for me next cycle. So because of that, I'm going to redo my decode, okay, in the next clock cycle. And the control signals that I'm going to write to the decode execute register are all 0. So what was here was going to be an and, but it became a no-op. And now I'm redoing my and. And now because I've stalled by 1 cycle, and I am also redoing the fetch here, when I go to execute, the data is ready for me from the load. Right? And then because I stalled this instruction, this OR instruction was also stalled. So for the OR instruction, that's also reading from register 2, the data is ready at the register 5 as well. And then from the OR, from the AND to this add, we still have this forward as well. This was our R-type forwarding that we covered already, right? And no stall is required. Okay. So our load word hazard detection needs to check when the ALU is being decoded in the instruction decode stage. And if the ALU operand register numbers in the decode stage, RS and RT, right, match the RT register of the execute stage, and the instruction in the execute stage is going to read from memory, then we need to forward. Well, stall and then forward later, right? All right, so how to stall the pipeline? So we need to turn the instruction that is going to go into the execute stage into a no-op. We saw this on the data path diagram. Right, the hazard detection unit sets all of the control signals to 0. If all of the control signals are 0, even though the ALU is still going to perform some operation, and then it's going to go into the MEM stage and do nothing, because read signal is 0, write signal is 0, and then it goes to the write backstage. It does nothing because the write register, well, not the register, but the register write signal is 0, right? So in the end, by setting all of the control signals to 0, it's like inserting a null instruction for those last 3 stages. And we just redo our decode. And then in the next clock cycle, when we go to execute, we do our real execute. And the other thing that we need to do is stall. So this inserts the no operation. This is our stall. So we need to prevent the update of PC so we can redo fetch and prevent the update of instruction fetch and instruction decode register to redo our decode. So the instruction where we detected the hazard does decode again. The instruction behind it is fetched again. And we keep those same instructions in their decode and fetch stages. And in order to stop the PC and this pipeline register from updating, in order to perform this stall, we just set their write signals to 0. And if the write signals are 0, they don't update, they keep their old value. And by implementing this one cycle stall, it allows the memory stage to be executed and the data from the load word to be available in our next cycle once we're executed. So this is our not final. There's still a little bit more to be added to this pipeline, but we now have from the single cycle, we have the whole path. And then after the single cycle, we've added control, right? And after we added control to the signal cycle, we talked about pipelining and added these pipeline registers, right? And then on Monday and today, we've added this forwarding unit so that we don't have to stall as much. And then the hazard detection units for the case of load word dependency when we can't avoid the need to stall one cycle. Okay. So we're all comfortable with this picture. So our data hazards recap. If forwarding is not supported, there is a dependency between two consecutive instructions. You need to stall for 2 seconds. You can't forward, there's no way around it. You have to wait until that instruction is in its write back stage. Whether it's a load word or an R type or an I type that writes to the register file, it's 2 cycles. If forwarding and hazard detection are supported, then if it's an R format instruction or an I type that writes to the register file as well, so like and I, add I, sub I, all of these things, then you don't need a stall. Because after it's done with its execute phase, it has the data. Our next phase is execute when we need that data. So we don't need to stall, we can just forward. But if we have a load word followed by a dependent instruction, we require this one stall. Right? Because the load word doesn't have its data available for us until the end of the memory stage. So if we went into our execute stage when we normally would have gone, when load word is in its memory stage, we wouldn't have the data available to us. And we do this by stalling, and we stall by just redoing decode. And because we're redoing decode, the instruction behind us can't go into decode, so it redoes. All right, so this is your poll question for today. Your code is 108. Question is, how many values require forwarding? And do not trust the highlighting on the options. One zero eight. Good. And answer on your own first.
Did 108, correct?
Mhm.
That's waiting for presentation to begin.
Better? Okay. Don't see any new answers coming in, but they're not quite at the threshold. So do talk to the people around you.
Three of the values are 4 days. One, yeah, because we need the values registered too. And that needs to be sold at least 2 months before 4 days. So that one does, yeah. Yeah, we'll see a value. Or, we need to add or and then two. And yeah, there's, I just wanted to. If I look at 4, we need to 4 to complete. Ordering it to do the ask and stuff, so these would be 4. Forwarding.
Results. All right, we have more movement towards the right. All right, first cycle, we fetch load work. Okay. Second cycle, we fetch the and we decode the load word. Third cycle, fetch the OR, decode the AND, execute load word. And this is where we figure out
There's a hand.
there is a hazard that requires a solve. Okay. The load word is going to write, and you can read from memory, and the AND RS matches RT. So in the fourth cycle, we redo decode, redo fetch, load word does its memory stage, right? And then in the fifth cycle, we forward from the end of memory or more the beginning of write back to execute on the end. Right? And this is decoded. This is fetch. Then in the next clock cycle, and is in memory. Word is done. But it has written to the register file, right? We have this OR that's in execute. We don't need to forward to the two, right? Load word is done. It's been written to the register file. But we do need to forward 4 to 4. So this is our second forward. And then in the next clock cycle, where is AND? Right back. OR is in memory. Add is in execute. So we have this that we would potentially need to do, right? From AND to 4. But we also have from the OR 4 to this 4, right? And this one is the one we would pick. So it's 1, 2, 3. 3 fold. Right? Are we all good with this? All right. So this is E3. Then the next question is, how many cycles are required? Assuming we have forwarding and hazard detection. So everything that we've covered up until this point. How many cycles does this code? Don't see any new answers changing. We are again close to threshold, but not quite there. So do talk to the people around you again and.
What do you think is the? I think we were fine.
Something, and you're gonna start. Or if it's on the reads, and if it's I want to buy you as a written to the words. Okay. So it's this one. So it's like, let's get the value before.
If you change your answer, if you would like to change. So for this one, I'm going to use void and draw the multi-cycle diagram. So what goes on top? Cycle, right? Cycle 1. My instruction is load word. Cycle 1, load word does. Nothing else happens, okay? Cycle 2. My next instruction is an and. Load word does
Both.
and does
Fetch.
We
Execute.
execute load word,
Decode.
decode, and
Fetch.
right? And it's here in decode that we see the problem register 2, register 2, right? So to solve that, in the fourth cycle, load word proceeds to memory.
Decode.
I redo decode. We indicate that it's a stall with a clap for the bow. What does this one do?
Fetch.
And it is also a stall, right? And then cycle 5, we have cycle 5. I'm in right back. I can execute forward. Right, and we indicate forwarding with these arrows. This one is decode. And the add is fetched. Cycle 6. The load word is done, right? We're in memory. For this instruction is an execute. And like we talked about already, we don't need to forward from the load word to here, even though we still have register 2, because in cycle 5, the data from this write back is at the input of the register file and is already sent and read correctly to this instruction. But what we don't have is register 4, right? We read the incorrect register data here. We need the correct register data. So we need to forward. And this one goes to decode. cycle 7. We're in write back. This goes to memory. This goes to execute. Right? And in this execute phase, we don't need register 2, right? It was read correctly here. Load word was already done. But we do need register 4. And we already talked about we need the register 4 from here. Not from here. Okay. Just so we're clear, I'm going to erase it all. Then cycle 8. This is write back. This is memory. Cycle 9. This is write back. And we're done. Okay. So this is our multi-cycle diagram. And this is how we should indicate forwarding and stall.
For the hardware version of this.
And the hardware version is the only version I will ask you for. Because hardware version is the one that is info message. Okay. So what I don't want to see is load word, no op, and or add. Right? By looking at these 4 instructions, we can visually see, because we can see all 4 instructions at the same time, that we're going to need that stall. And the compiler would need to be able to see that too. But the hardware does not figure out the problem until cycle 3. Right? And here is the single cycle diagrams. Right? We have the load word, we have the and, we execute the load word, we figure out our problem, the decode of the and. This is the no op. That's what's indicated here, right? By redoing decode. So we redo decode, redo fetch. And then when we're in executes, we can forward the value from this register. And then we can execute normally. And then for the or, we forward from this register to get our correct register 4. And then for the add, we forward from this register because this is the newest value of register 4. Even though the and is also register 4, we forward the newest value of register 4 to the execute stage here. So here is your last question. This is a new set of instructions. Just asking how many stalls occur.
With forwarding.
Yeah, with everything. So forwarding, hazard detection. Everything that we learned. see is changing. We are not quite at the threshold again. So do those people around you discuss what is occurring with the question? If it's helpful, draw the multi-cycle diagram, right?
Right, one mandatory stall. And then for the rest, do you feel like we need any stalls, or do you think boarding takes care of the rest of the factors? I concur. Mandatory stalls. All the boarding, you will take it, potential. One players.
Do you change your answer if your parents change your answer? Okay. So I will tell you guys, we are not where I would like to be at for this answer. I would like to see this number to be around 85, 90% after a peer discussion. So do spend some more time understanding the forwarding, hazard detection, pipeline architecture. So this is B. The reason is this load word is dependent on the add. But the add is done in execute. Load word doesn't need the value until execute, so we can just forward. No need to solve. This and is dependent on the load word and the add. But again, we can just forward from here, but we can't just forward from the load word, right? So we need to stall for this memory instruction. So this is my one stall. And then after that stall, I no longer need to forward from this 3 to this 3. It will just be written to the register file, and I'll read the correct value when I redo my decode. But I will still need to forward 4 to 4. Okay. And then from this and into this sub, we can again just forward. This is done in execute. This isn't needed until execute. Let's just forward. And then this 6 is also forwarded to this 6. Right? So this is just one stall, right? So it's B1. One stall. And then here's another question. How many values require hardware forwarding support to avoid stalling for our MIPS 5-stage pipeline? We talked about this. 1, 2, 3, 4. Right? Right, so here's a short recap. We improved performance by increasing instruction throughputs. Because of this, we have multiple instructions in our pipeline at any given time. So we have these 3 types of hazards. Structural hazards occur when you want to use a shared resource. Data hazards occur when we need to wait for a previous instruction to complete some part of its execution where we're dependent on that data and that result. And the next time on Monday, we're going to start talking about control hazards, which is our branching, jumping, things like that, right? We can't do the next instruction after a branch until we know what the result of the branch is, because we don't know what is the next instruction, right? So we're going to talk about how to handle that and some clever ways to actually start executing the next instruction without knowing the result. So your reading for that is chapter 6.7. That will be due on Monday. And I'll try to grade your exams before Monday.
Okay.
As well as homework. The other thing is, today was the last day for updating your preference of order for the presentation. So today I will finalize that. And I'll update the post on Piazza as well with the final presentation order list.